Hello everyone, my name is Soumya Das and today I am going to be discussing about the topic pointer aliasing. The first slide is about what is pointer aliasing. Pointer aliasing is a situation where the same memory is allocated using two different names. For example, if I take two pointers A and B, then the name A0 aliases the name B0. This would mean that A and B are aliasing each other. We are now going to discuss about the types of pointer aliasing. Our first one is strict aliasing. Here, when two pointers of different types cannot refer to the same location, it's called strict aliasing. Compiler assumes that the pointers of different types do not alias and enables aggressive optimizations. The second one is type-based aliasing. Here, the two pointers of the same type refer to the same memory location. Compiler in this case can optimize based on the assumption that the two pointers do alias. The third one is a condition, may alias. Compiler in this case does not know or cannot determine whether the two pointers will refer to the same memory location. In this case, compiler avoids aggressive optimizations which assumes two potential aliasing. Now we are going to discuss about the effects of pointer aliasing. The first one is optimization issues. Pointer aliasing can hinder compiler optimizations, making the code inefficient and slower. The second one is undefined behavior. In this case, pointer aliasing can lead to undefined behavior, making the program unpredictable and unreliable. Modifying the same memory location through different pointers can result in an unexpected result. The third one is debugging challenges. Identifying and resolving pointer aliasing issues can be complex and it's not easy, resulting in difficult to debug errors. Aliasing related bugs may manifest in unpredictable ways, which makes them harder to diagnose and fix. Let's understand strict aliasing. Strict aliasing is a type-based aliasing rule where two pointers of different types cannot refer to the same memory location. For example, consider an int pointer and a float pointer pointing to the same memory location. Compiler optimizations. Strict aliasing allows the compiler to assume that the value accessed through the pointer do not affect each other. Here there are optimization benefits. The compiler can perform aggressive optimization which can improve code performance. Let's see the common examples of pointer aliasing. The first one is global variables. Multiple pointers can accessing and modifying the same global variable. Different modules or functions may have separate pointers to the same global variable. The second one is function parameters. Aliasing can occur when pointers are passed as function parameters. Functions modifying the same memory location through different pointers. The third one is structures and unions. Aliasing can happen within structures or unions containing different pointer types. Accessing and modifying the same location through different fields of structure or union. How do you mitigate pointer aliasing issues? The first one is use strict type-based aliasing. Avoid mixing pointer types that may alias with each other. Ensure that different pointer types do not point to the same memory location. The second one is to restructure the code. Modify code structure to reduce the chances of pointer aliasing. Separate data accessed by different pointers to avoid aliasing situations. Third one is to use compiler flags. Enable compiler flags to enforce strict aliasing rules and improve optimization. For example, "-fstring -aliasing". This is a compiler flag that helps to enforce strict aliasing rules. Here we are going to discuss about the different ways in which the compiler helps in preventing pointer aliasing related issues. The first one is compiler optimization options. Many compilers provide optimization flags to handle pointer aliasing more effectively. One of those optimization flags is "-fstring -aliasing", as we have seen in the previous slide. It helps the compiler to make better assumptions about aliasing. The second one is compiler specific extensions. Compilers have some specific or offer some specific extensions or attributes to declare pointer aliasing relations explicitly. Annotations or attributes can indicate when aliasing is intended or prohibited. Let's discuss about the best practices. The first one is avoid excessive pointer casting. Casting pointers to unrelated types can introduce aliasing problems. Use constant qualifiers as the second one. Declaring pointers as constants can help in preventing unintentional modification and aliasing. This is because constants have a fixed value. The third one is to understand the compiler's behavior. Familiarize yourself with the compiler's documentation and behavior regarding aliasing. Each compiler may have its own rules and optimizations related to pointer aliasing. We are now going to be discussing the different examples of pointer aliasing using program codes. First one is aliasing of int and float pointers. Refers to a situation where a pointer of one type, either int or float, is used to access and modify a memory location that is interpreted as the other type. This can lead to potential issues and undefined behavior in the program. Let's consider this example. In this code, we have an int variable num initialized with the value 10. We then create a pointer float ptr of type float star, which points to the memory location of num but is interpreted as a float pointer. Now we assign the value 20.5 to the memory location pointer to by float pointer. This modifies the underlying binary representation of the int value. Finally, we print the modified int value and interpret the memory location as a float to print its value. The potential issues arise due to the mismatched interpretation of memory contents. In this example, we treat the int memory location as a float and modify it accordingly. However, the underlying representation and storage requirements of int and float differ, leading to undefined behavior. The issue with aliasing of int float pointers can affect optimization performed by compilers. Compilers often rely on strict aliasing rules to optimize code. Strict aliasing assumes that pointers of different types will not point to the same memory location. When such assumptions are violated, optimizations based on strict aliasing can result in incorrect behavior or unexpected results. Additionally, the behavior of the program becomes undefined due to the mismatch between the actual type of the variable and the type used to access it. The behavior can vary across different compilers and platforms. It may produce incorrect output, crash the program, or lead to other unpredictable consequences. Here in this code, we have a function called swap that takes two integer pointers as parameters. Inside the function, the value pointed to by the pointers are swapped using a temporary variable. In the main function, we declare an integer variable x and create a pointer p that points to x. We then call the swap function passing p and the address of x as arguments. Even though we expected the value of x and star p to be swapped, they remain the same. This happens because p and the address of x are aliases. They point to the same memory location. When swap modifies the values using the pointers, it affects the underlying memory location, which is accessed both through p and $x. This example demonstrates how aliasing in function such issues can be challenging because it may not be immediately apparent that the pointers being passed to the function are aliases. The code may appear correct, but the actual behavior is different from what is expected. When debugging aliasing related issues, it can be helpful to carefully examine the code flow and ensure that pointers passed as function parameters do not unintentionally alias with each other. It's important to track the memory location being accessed and modified through different pointers to identify any potential aliasing problems. As I reach the last slide, I would like to thank you for watching. Hope this was informative.